Welcome everyone to the Control Meets Learning seminar. Today we're delighted to have Professor Sasha Rakhlin from MIT. Sasha is a leading expert in statistics, machine learning, and optimization. He's an associate professor at MIT with joint appointments in the Statistics and Data Science Center at IDSS, as well as the Department of Brain and Cognitive Sciences. He is the chair of the interdisciplinary doctoral program in statistics at MIT. And he got his bachelor's degree in mathematics and computer science from Cornell, and then his doctoral degree in computational neuroscience from MIT. He was also a postdoc at UC Berkeley EECS before joining UPenn as a faculty member. He was an associate professor in the Department of Statistics and a co-director of the Penn Research in Machine Learning Center, the PRILM. And he has done many significant contributions in statistics and machine learning, which has garnered numerous awards, such as the NSF Career Award, an IBM Research Best Paper Award, a Machine Learning Journal Award, and a Colts Best Paper Award. Today, we are very excited to hear about an interesting connection between contextual bandits and online regression, and we're delighted to have him. So without further ado, Sasha, the floor is yours.
Thank you very much, Navid, for this nice introduction. Thanks for the invitation. Delighted to speak here. So I will describe two papers, results from two papers, one with Dylan Foster, and that will take maybe 2/3 of the time. And then the next one is a joint work with Dylan Foster, David Simchilev, and Yunzong Shu. So just to put faces to the the names, Dylan Foster is a postdoc at MIT, and he has done essentially all the work that I will be describing in the first 2/3 of the talk, and then the last third will be joint work with Dylan and Yunzong and David, also at MIT. And in particular, I want to highlight Yunzong, who is an amazing third-year undergraduate. Sorry, graduate student. So I'm going to describe, start from the beginning. I'm going to describe the problem of contextual bandits. I apologize if you know the problem. I will start a little bit slow and ramp up. So in this problem, the agent or the learner interacts with the environment. At each round T, the decision maker receives some context XT, selects an action AT, and observes the reward RT. So this might look like a problem in reinforcement learning, and it would be if the actions affected the state XT. But in the problem of contextual bandits, we will assume that the actions do not affect the next context. And so we will call it the context rather than state. So the problem is ubiquitous. One common application is in medicine or randomized trials, where the context can be the medical history of the person that comes to the doctor, and the action is the treatment prescribed by the doctor to the patient, and then the reward is whether the patient got better or worse. What we would like to do is, over multiple interactions with different patients, to learn which actions bring more reward. Another application is mobile health, where the context could be the current state of the person who, let's say, is trying to quit smoking, or maybe trying to lose weight or whatever and do more exercising. The action is some kind of intervention done by the program, by the iPhone or by a watch. And then the reward is whether the person did change the behavior. And of course, the most obvious application is in advertisement, where the context is whatever the system knows about the person, browsing history. The action is a choice of an advertisement or a choice of products, multiple products or a single product. And then the reward is whether the person clicked on the advertisement. Another application is in online education, where the context is the current information about the student, action is the next exercise, and the reward is whether the exercise was too easy or too difficult. Okay, so in my mind, there's a hierarchy in terms of the difficulty. Of course, these are not necessarily comparable, but supervised learning is the problem that we understand very well. This is where we observe data passively, and typically data comes from an IID distribution. The problem of contextual bandits is more difficult in the sense that the actions are required for getting the data that you want. So there's an element of active data collection in contextual bandits. And reinforcement learning is even more complex because the actions actually change the state, and that requires some planning. There's quite a large gap between, at least to my understanding, between supervised learning and contextual bandits and reinforcement learning. And especially I'm interested in understanding function approximation and what are the relevant measures of complexity. How many samples does it take to either provide a pack type of guarantee or a regret guarantee in these setups. So the aim of the most of the talk is actually to try to close the gap from supervised learning to contextual bandits. And I will, if there is time, I will describe a little bit in terms of reinforcement learning, but there is a lot of work to be done there. Okay, so let me describe the contextual bandits. Suppose that we have these treatments or items, and in the usual multi-arm bandit problem, we model the quality of these items or quality of these treatments as a distribution over a reward with certain means. The means are horizontal lines here. And the goal is to one by one discover which treatment is the best here, for instance, the watermelon. But of course, this depends on the particular person. So this person might prefer watermelons to other treatments or other choices. Another person comes and the order of the means switches in some way. And so the goal is to actually borrow strength to gather all the information about different individuals to learn the preferences of different people. So I like to think about this as a two-dimensional plane where on the one axis we have the context, the information about the person, the covariates that should help us in determining the means of the arms. And then on the other axis we have the products or treatments. And so for one person, that's the picture that we had on the previous slide. And if we track the mean of the reward distribution over the individuals, then we have some function, maybe looks like that. And for another treatment, we have another mean and so forth. Okay, so you can think of this as a two-dimensional surface. On one axis, we have a potentially high-dimensional covariate X, the context, and on the other axis, we have the action, which can be finite or it can be infinite. For this talk, it will be a finite set of actions, 1 through k. So the problem is to leverage the information, the structure of the function to learn this unknown function f. And coupling is not just done on the level of the context, the mean as a function of a context, it's also done as a function of the actions So there could be some actions that are more similar than others. Okay, so mathematically for t from 1 to n, so I apologize if you're used to t being the time horizon. In this talk, n will be the time horizon. For t from 1 to n, we will observe the context xt, that's the person, choose the arm at, that's the treatment, and then observe the reward for the chosen arm. Okay, so that's the problem of contextual bandits. We will make the following assumption. We'll assume that we have a class F such that the mean reward when you choose action AT in context xt, that mean reward is described by some function f star, which belongs to this class. So this is a realizability assumption. And what we would like to do is we would like to take a rich class of functions, F, say class of neural networks, generalized linear models, decision trees, kernels, what have you, and just run a off-the-shelf method for contextual bandits with that class. And this doesn't seem to exist, although people do use some hacks in practice. But this just shows the gap between how much we know about the supervised learning versus the seemingly very similar problem of contextual bandits. What's the measure of performance? It's expected regret, will be denoted by regCB. It's the expected difference between the cumulative reward of the optimal action for each of the contexts and the action that we actually chose. Okay, so this is the gap between what we've done. We're maximizing rewards, so this is what we've obtained versus what we would have done if we knew F star and we would be able to choose the maximizing action. So this is a very natural notion, expected regret. Why is this the right notion? Well, in medical trials, regret is really the treatment quality. So you would like to not spend too much time giving suboptimal treatments to people. You would like to learn as quickly as possible, and that's quantified by small regret. In recommendation systems, regret is really the revenue that you lose by choosing suboptimal actions. In mobile health, you have patient attrition and so forth. Okay, so what is the goal? The goal is to develop general purpose methods for contextual bandits. We do not want to design a new algorithm for each new class F. And hopefully, and this is a kind of a grand goal, is to have an algorithm that's not much harder in terms of computation than supervised learning with class F. So if we could achieve these desiderata, then we would close essentially that gap between the supervised learning and the contextual bandits. So why is this problem difficult, and why I argue it hasn't been solved in this full generality at the level of supervised learning? So it's well recognized, and again, I apologize if this is very obvious to you. The difficulty is that we have bandit information. We have no counterfactuals. So when this particular person appears, we know the context, we know the medical history, or whatever the history about the person, and we choose the tomato, we receive a noisy version of this red dot and a noisy version of that value, but we don't know any other points on this line. And we might not see the same covariate xt twice, right? So unlike the multi-arm bandit, where you can think of fixing a person and just playing for a long time with that person, choosing the different actions, experimenting, here we don't see the same person twice. We might not see the same person twice. And so we cannot treat every context as an independent multi-arm bandit, and so we have to borrow strength and extrapolate. The difficulty is that it's unclear how the information propagates. So if we receive this information for this person upon choosing the tomato, it's unclear how the information about this value propagates to other people and other actions. In particular, I'm mostly interested how this information propagates to other people, other contexts. And so you can imagine that if you assume Lipschitzness or some kind of smoothness, then you can say something about the local neighborhood. But beyond that, it's unclear. If suppose that I know that this unknown class, unknown function f, which should be f star, given my previous notation, if I know that this f star is a neural network, how do I know how does this information propagate? This is very unclear. And this is in stark contrast to supervised learning, where we can choose whatever expressive class you want, and we understand very well sample complexity for essentially every class F. Okay, so what's the typical approach to multi-arm bandit problems, and can we lift it to contextual bandits? So upper confidence bound is the method that was proposed in the 80s. Lyon Robbins, 85, is a classical paper with this method. Essentially, you start building, this is for a fixed context, for a fixed person. You select these arms as follows. You start building confidence intervals, and then you go for the upper bound of the confidence interval. And that what that does is it combines exploration and exploitation into one go, because you either choose let's say the corn because the mean was large or because the uncertainty was large. So you decrease uncertainty, or you don't suffer much regret. Okay, so it's a single method that works. So can we lift this to general function approximation problems? Well, you would like to say, okay, I'm gonna try to estimate y hat and build some kind of, you will try to build an estimate y hat of this unknown regression function f star, and you will try to build confidence intervals. So the issue with this approach is that in general, there is no hope of constructing valid confidence intervals for each XA pair. This is something that's well understood in statistics. Of course, with some exceptions. So linear classes, generalized linear models, or binning type methods where you pay exponential in the dimension, but you can treat every little bin as a separate multi-arm bandit problem. So if you're talking about neural networks, I don't see any way of providing confidence intervals for x comma a pair that would be valid for all x comma a. And so another issue is that, and I'm repeating maybe myself, that we can only estimate f star. So this y hat can only estimate f with respect to the distribution induced by the policy. So we're using a policy to collect data, and then if the policy misses some part of the space, not sampling XA pairs in some part of the space, then the quality of this estimate cannot be too good. Moreover, we don't typically have pointwise convergence of the regression estimate, for instance, to the true regression function. We only have kind of on average L2 type of convergence. And other methods like inverse probability weighting lead to high variance and generally suboptimal regret. Okay, so this is a very brief mention of past work. If your name is not on this, I apologize. There's a lot of papers on contextual bandits. I just want to highlight methods or settings where we know kind of clearly what to do. So in the linear case, you can lift the upper confidence style method and have a nearly optimal performance. You can generalize it to generalized linear models, and there is work on non-parametric holder methods. There are more from 2020 as well that I didn't mention here. Okay, so and so because of this kind of large number of papers on different classes of functions, I should speak for myself. I definitely thought that optimal exploitation has to depend in some intricate way on the structure of the class F. So if you choose neural networks or decision trees, the kind of the way that you should be exploring and exploiting should somehow leverage that structure. And thankfully, somehow we were wrong, and this is exciting because what I will present to you completely decouples the problem of exploration from the intricacies of the class F. Okay, so what is the algorithm? The algorithm is as simple as you can imagine. We call it the square CB algorithm, and this is the paper with Dylan Foster. By the way, I should say that Dylan is on the market and he is amazing, and all of this work that I'm presenting is really due to him. So for t from 1 to n, you receive the context xt. You somehow compute reward estimates. I'm going to just postpone this discussion for a second. Suppose you compute reward estimates for the current context xt and each of the actions a1 up to ak. So there are k actions a1 through ak. And let's say you build somehow reward estimates for all of them. Okay. Then what you will do, what the algorithm square CB does is it creates the following randomization distribution over these k actions. We call it the inverse gap weighting, IGW. So you look at the best arm B. So this is the best reward estimate, the highest estimated reward. Might not be the true highest, but according to our estimates, that's the best. And then for every arm that's not the top estimated arm, you create the probability distribution as very simple 1 over k, the number of arms, plus a scale times the gap between the best arm and the whatever quality of the arm A is. Okay, and the best arm gets the remaining probability. Okay, it's a very simple procedure. Yeah, hopefully this is clear. Then the decision is just to sample from this probability distribution, observe the reward RT for the chosen action, and update the model with the triple XT AT RT. Okay, so the method should be hopefully clear, except I didn't tell you how to compute the reward estimates. Okay, and I didn't tell you how to update the model with this triple. So these are the two parts that I need to describe. Okay, so where is this inverse gap weighting method where is it coming from? Well, actually, one of the first, if not the first paper on contextual bandits by Abe and Long in 1999 was using this randomization procedure. And as you can see from Scholar, it has 45 citations, which is about 2 days worth of citations for a modern machine learning, NeurIPS paper. So this is really something that has been just under the radar, but that's the one that proposed this procedure. So what are the key, and I will come back to kind of and explain where that method is coming from, if you're interested. So what are the key features of this square CB method? What can we prove? So what we showed, this is the 2020 ICML paper, that we can, if we form reward estimates y hat using online regression, which I'll describe in a few slides, then the square CB method is minimax optimal for any f. One thing that I didn't specify yet is that we will not assume that the covariates, the contexts come as IID sequence. This result works for arbitrary sequence of context. And moreover, the square CB method has the same computational efficiency as online regression, maybe at times number of arms k. Regret degrades gracefully with model misspecification. I'll mention all these results in more detail. As I just mentioned, x1 through xn can be arbitrary. We don't need an IID assumption on the data. And what's remarkable is that reward estimation part, which is done by online regression, is completely decoupled from the decision-making part, which is done by the randomization distribution. Okay. By the way, if there are any questions, please feel free to interrupt me at any time. I don't mind being interrupted.
Yeah. I don't see any questions on the chat yet, but if anyone has any questions, please feel free to raise your hand or post on the chat box.
Thanks. Okay, so let's go a little bit more into the technical details. So what is online regression if you haven't seen it? One of the first papers for square loss online learning is by Dean Foster in 1991, Annals of Statistics. This proposes a method that works for an arbitrary sequence of data, x1, xn, as I mentioned, and also the responses y1 through yn, for the linear model. So if the class is a class of linear functions, then this proposes I believe this is the first result of this type. Dean says that he had trouble publishing this for a few years because the statisticians couldn't believe that one can do something for an individual sequence, for an arbitrary sequence. But so that this is something that's now well understood. There is a book by Cesabianchi and Lugosi on online learning, and I will refer to that. So what is the general online learning problem? For t from 1 to n, suppose that we receive a zt, some abstract piece of information, zt. We compute the prediction y hat t. Let's say it's bounded 0, 1, doesn't matter. And then you observe the outcome yt. Okay, so that's the protocol for online learning. And then in online regression, you are interested in minimizing regret with respect to square loss. So the first part is what you pay in terms of how well you predict the next outcome after observing the ZT, and that's cumulative over n rounds. And you compare yourself to how well you would have done if you knew the best function f in this class. And you compare your loss to the loss of that predictor. And we will denote the regret that you get by regsq, regret with respect to square loss. And that, of course, depends on the class f. If the class f is more complex, then you would pay more. And of course, this quantity also depends on n and kind of how the complexity of f results in the growth with respect to the number of data points. Sample complexity is exactly the question in this field. And importantly, what you would like to guarantee is that this regret holds for any sequence z1, y1, zn, yn, without any generative assumption on the sequence. It's an arbitrary sequence, individual sequence result. So I've been looking at this problem for a long time with different loss functions. And in 2014, I can refer to the paper with Kartik Sritaran. We have a full characterization of optimal regret for any class f. So we know if you take a class f, we know exactly how to compute the growth of minimax regret in terms of number of data points. And when we do the conversion of this online regression, which is essentially an online supervised learning problem, the ZT will be a pair XT-AT. So that will be the conversion. So let me show you this conversion. An equivalent way of estimating, of stating online regression is as follows. You receive the ZT, and then you compute the function y hat t of ZT. Now you can think of computing this function for arbitrary input ZT if you're able to run this algorithm. And then you update your function. So this function is, think of this as not just a single prediction, but a whole function from Z to this interval 0, 1. And so we will run the online regression on the sequence x1, a1, r1. So r1 will be the target y, the yt. And the first two arguments will be the z. And so what we will do is when in the contextual bandit problem, when we're at time t, we're being asked to estimate the values for the k actions, we will compute these estimates using this online prediction strategy. Okay, so these are the online regression estimates that we have. All right, does that make sense? Any questions? Okay, so I told you how to compute the estimates. Let me just say a couple of things about the second ingredient. So that was the first ingredient. The second ingredient is this randomization procedure. So this randomization procedure, this is just a map from the reward estimates, the scores, 0, 1 to the k, into the probability simplex. There are a gazillion different ways of doing this map. So why this particular map? It turns out that this inverse gap weighting approximately solves the following min-max problem, or min-max-max problem, which provides an interesting link from the contextual bandit loss to the square prediction loss. So let me try to unpack this displayed equation. Hopefully you can see my mouse pointer. So the question is, conditionally on xt, so suppose that you've observed the xt, the context at the given round. Are you able to select a probability distribution, and think of this as this particular one, this particular probability map, such that no matter what the optimal action is, A star, we don't know what it is for the given context, but whatever it is, and no matter what the truth is, what the true value for the means of all the k arms is, when you randomize according to this probability distribution, you can bound, hopefully you can upper bound this whole expression, you can bound the difference between the contextual bandit loss, which is precisely this. Oh, sorry, this is minimizing. So I wrote this as this is being smaller than this. So, sorry. So just switch the two places. If we're doing rewards, then you need to switch these. So f a star minus f a minus the quality on average of the estimate of the true value of that arm by whatever the procedure you have. And so this is a statement conditionally on the scores. So this is a really surprising, just really surprising thing, that you can link the contextual bandit loss to the quality of the estimate, no matter what the best arm is, and no matter what the true regression values are for a fixed vector of scores. Okay. Now the upper bound on this min-max value is achieved by the inverse gap weighting, and that achieves 2k over gamma upper bound on this. And there is actually an exact solution that would take you not much time to derive, and that's actually a log barrier minimization. So think of this like a mirror descent with a log barrier. And that gives you the exact value of k minus 1 over gamma for this min-max problem. Okay, so there's a new paper by Dylan Foster and co-authors that fleshes out this optimization point of view on this randomization procedure. Okay, a little bit behind. Right, so the main result in that paper is that if you have an online regression oracle, then the square CB algorithm guarantees regret at most square root of k, the number of arms, and the time horizon, and whatever the regret that the square CB was getting. Right? So we're able to link the regret in the square CB problem to the regret in the online regression problem. And this holds for an arbitrary sequence of contexts. So this is a robust result in terms of the presentation of these covariates contexts. And moreover, they can be adaptively chosen. So if you have some reason to think that, as patients come into the doctor, somehow the composition of the patients changes, it's not a fixed distribution from which they're drawn, then maybe this result is more interesting. Okay, if there is time at the end, I can go through to the proof sketch. So it's easy to apply this genetic theorem. So for instance, if you have a finite class, we know this is a gosh, what's the first one is probably by Vovk on the mixable losses. So okay, I don't remember anymore the first reference on this. So the regret of a procedure against the finite collection of expert with respect to square loss is at most log cardinality of the class. And that just directly implies that the regCB, the regret for the contextual bandit problem, is square root of kt log cardinality. And I'm just going to skip the log n factors here. If you take linear models, so for instance, this is a linear model for the contextual bandits, then you have two choices. If you take an online regression method to be online least squares, then regret is at most d log n. I'm skipping log n here, and that's given by the Vovk-Azuri forecaster, or essentially it's in the Dean Foster's paper that I mentioned before. So if you do that and you plug it in, you get square root of k and d up to log factors. And the runtime here is k/d squared because you have to form this covariance matrix. Then another choice, which is faster, that is just to do a line gradient descent on the square loss. In that case, under the appropriate kind of norm boundedness of the iterates and the x's, you get the upper bound on regret of square root of n, and that gives you square root of k n to the 3/4 for the overall square CB method for the contextual bandit. And that's faster because it's k times d per step. It doesn't form the second order information. Okay, so more generally, it's optimal. So if you take any class f, that the square CB method will be optimal. So let me just quickly mention that. Okay, I'm not going to define the covering numbers, and this result is okay. Look, if you're interested, look in the paper for more detailed comparison. But because we understand the optimal regret for online regression, and that's not in terms of covering numbers, but in terms of sequential covering numbers. But okay, let's forget about that. So the classical fixed point is given by this balancing equation that in statistics, this goes back to Lecam and okay, so forth. Then square CB has this particular rate where epsilon n is that fixed point, and no algorithm can do better than that. Okay, so I'm just going a bit faster. Robustness and misspecification. If the true rewards are epsilon away from the class F, so you have L infinity kind of epsilon misspecification, then performance of square CB degrades linearly with epsilon. So you get epsilon times n times square root of k. I think this is the first known algorithm with such a property for general classes of functions. So how does it do in the experiments? Dylan ran these large-scale experiments, duplicated the experiments on 500 data sets by Bieri et al., and included the square CB, and he pushed the code into this Vobel-Wobbit framework now. So the results are encouraging. SQ is the method that I just described, and it wins against the positive numbers is good for this method. It wins against all the methods except for the regCB optimistic, which is a result previously by Dylan and co-authors. What I will get to next is the ADA-CB, an adaptive method that takes advantage of the gap between the best arm and the next best arm. And that beats all the methods that we know, including Thompson sampling, including epsilon greedy, Boltzmann, cover, online cover, and so forth. Okay, so I should say that we only looked at data sets with more than 3 arms, which is kind of the interesting case. All right, so so this is now in the Wobble Wobbit, and you can run that code. Now, next, let me mention the work by David Simchelevi and Yunzong Shu. 2 months after we put our results on archive, they extended our results to offline regression. So this is where you form y hat t's as just least squares. So simpler to state than online regression, least squares on the past data. Then you compute the scores as you would guess, just predicting the score of the quality of the arm within this context for all the arms. And then you randomize with the same strategy that we proposed, maybe slightly different learning rate. So the pros is that the model y hat t can be only occasionally updated, only logarithmically in n over horizon of length n. And the reason for that is that data are IID. And the drawback is that this result only works for IID data because it leverages the fact that uses the fact that the data are IID, so you can do least squares. And it's a basic ERM principle. So this is a very nice result. And the proof is very cute, very nice. And so I highly recommend to look at that. All right, so this inverse gap weighting strategy is kind of special. It allows you to do this kind of change of measure argument, in which the variance of the policies is bounded according to their regret, kind of a self-referential type of argument, and the result is by induction. So again, I encourage you to look at that result. Okay, so let me now turn to adaptive methods. That's the second part of the talk. And the question here is whether there is a contextual bandit method that does better in high SNR. So the results that I've presented so far are minimax optimal in the sense that if you go over all the probability distributions, you cannot do better with that class F. But it could be that in some cases, you can do better under the particular restrictions when the signal-to-noise ratio is high. So what is the signal-to-noise ratio? Well, if we look at multi-arm bandits, we know that minimax regret is square root of kn. K arms, n is the horizon. But the adaptive rate that depends on the particular gap between the top arm and the next best arm, denoted by delta here, is k log n over delta. So this is the well-known result that goes back to the 80s, right? So clearly, under particular assumptions on the distribution, you can do better than the minimax rate. And the question is whether this extends to contextual bandits. So the natural guess for contextual bandits would be that you get log cardinality of f times k log n over delta. So you pay k log n over delta for a single multi-arm bandit, and somehow if you've got a class of functions f, then you should pay an overhead of log cardinality f. Right, this would be a natural guess. And here delta is a uniform gap in the sense that for any x, when you look at the best arm, the mean reward of the best arm pi star at x minus any other arm, this is lower bounded by delta. Okay, any questions about this? All right, so it turns out that this is not possible, and you can find the argument in the paper with Dylan. This is not possible in general. So there exists f such that regret is at least cardinality of f divided by delta. Right. So this result works for either adversarial or IID context. So for adversarial, it's clear. One can choose a sequence of covariates, the contexts, and for IID, there exists a distribution and a function class such that this holds. So clearly, one has to make further assumptions about the instance. And this is why the results are called instance dependent, because they look at the particular instance and try to be adaptive to the niceness of the particular problem. So from now on, I will only focus on the IID contexts. So just like in the work of Yunzong Xu and David Sincelevi, I'm just going to look at the context coming from some distribution P. Let's define the class of induced policies. So given the class of regression functions F, you can define the class of induced policies, which are just the argmax policies for each F, right? So take the best arm for each F. And let's look at the following object. So this is a set of policies that are epsilon away from being optimal. In other words, as you look at the measure of the x's for which pi disagrees with pi star, if that measure is at most epsilon, then include that policy, right? So it's a class of near optimal policies. Then let's define the policy disagreement coefficient to be the ratio of the following measure. So it's a measure of x's for which there exists an epsilon optimal policy that disagrees with the pi star. Right? So rather than fixing pi here and then looking at the being close to epsilon, we're asking, let's look at the measure of the x's where there exists, for that little x, there exists some policy that disagrees with the optimal. And let's look at the ratio of that measure to epsilon and see how that behaves as a function of epsilon. What is the meaning of this theta? We call it the policy disagreement coefficient, denoted by theta POL policy. And the meaning of this disagreement coefficient is how likely we are to encounter a context X on which some epsilon optimal policy disagrees with pi star, and look at that relative to epsilon. Right? So the issue with the lower bound on the previous slide, the impossibility result, was that as you get more contexts, there are too many degrees of freedom where you haven't seen data, and you get surprised with too many x's, right? The aim of this policy disagreement coefficient is to put a restriction on how much disagreement there exists when you start getting close to the optimal policy, right? And let me just mention that this is the analog of the disagreement coefficient from active learning, which was introduced by Steve Haneke in 2014 in the active learning literature. But actually, it goes back to the 80s, and it's called Alexander's capacity function in the empirical process theory. And so this, the disagreement coefficient in active learning is known to improve the rates of passive learning by removing a log factor, but it plays a much more crucial role in active learning where it can have an exponential speed up, lead to an exponential speed up. Pictorially, this is the meaning of, if you like pictures, this is the meaning of this disagreement coefficient. So suppose that pi star is a binary function 0, 1, or a policy is just the choices of two arms, 0 and 1, and pi star is identically 0. So that's the, always choose the 0 action. And then let's look at this particular pi. Now it deviates a little bit from pi star, but suppose that the measure of this is epsilon, right? So kind of the deviation from the pi star is only on a set of measure epsilon. But there could be another pi star, another pi that's also close, but you know it's different on a different region. And what the disagreement coefficient does is it collects the measure of all these disagreement regions in the X space, and the measure of that relative to epsilon is the coefficient. Okay, so the result that we have, this is the first result in this long paper, Foster, Sincelevi, and Xu, that a method add SCB, which I haven't yet presented, I will do that in a few slides, ensures expected regret, choose the best epsilon scaling, and look at the max between epsilon delta n and this disagreement coefficient k log cardinality divided by delta. So maybe hard to interpret. Let's look at the worst case. The worst case, of course, for this disagreement coefficient is a 1 over epsilon dependence, right? Because the disagreement coefficient is probability divided by epsilon. Probability can only be at most 1. So the worst case is 1 over epsilon. Then you get exactly balancing of these two terms, and that gives you the minimax rate. In the best case, the disagreement coefficient is either a constant or maybe polylog in 1 over epsilon. And then you get the fast rate, which is our hypothesized rate for the contextual bandits with a class F. Please note that I'm only talking about finite classes F here, but everything extends relatively easily to not finite, but infinite classes of F. Right. So the goal here with a finite class is to get logarithmic dependence on the class F. Now, no algorithm can do better. So given the parameters, such as the number of arms, the gap, the scale epsilon, and the disagreement at that scale, there exists a class F and the distribution such that the gap is delta and the regret is lower bounded by this quantity, which is exactly this these two quantities. It's known, we can look at the literature on disagreement coefficients, and there are many known cases with small disagreement coefficients, linear functions with log concave distribution, depth limited decision trees, and so forth. So this is really a fundamental quantity that is relevant not only for active learning, but also for contextual bandits. Now, in fact, if you look at the paper is quite long, and the reason for that is we try to put together many different quantities that have been considered in the various parts of the literature and provide kind of a comprehensive picture. So let me describe the result. What I talked about so far is a policy disagreement coefficient. That's a non-scale sensitive version. It just looks at the policy space and discrete actions, A1 through AK. Now you can actually look at the value function disagreement coefficient, where the scale of the regression function starts to matter. And that's a generalization of the policy disagreement coefficient. And we show that these results are, these quantities are fundamental to the instance-dependent regret for contextual bandits. In the distribution-free setup, if you don't know anything about the distribution, there is something called the policy, something called the star number in the active learning literature. Again, defined in papers by Heinecke and co-authors. And so we extended to a policy star number, and that can be seen to be an upper bound on the distribution-based quantity. And the scale-sensitive generalization is the value function star number. And then once we go to the adversarial presentation of the contexts, there is a Luder dimension introduced by Russo in was it 2013, and Ben Van Roy, sorry. There is a scale-sensitive version of that Luder dimension that can be defined, and so this is the overall picture. And all of these are necessary and sufficient under appropriate assumptions, but also there could be infinite gaps or very large gaps between these quantities. So the best one is, of course, the kind of the distribution-based quantities. Let's see, I don't have time to go into the scale-sensitive generalization. Let me just say that it's kind of what you would expect. It's the measure of the x's under the distribution on the x and the a, such that there exists a function that is far on that xa pair from f star, given that you're in an epsilon ball around the optimum. So it's a natural generalization. And this is simpler to bound in some cases when there's structure of the class F. And for instance, for the linear classes, this value function disagreement is bounded by the dimension, but you can get similar results for this link function applied to the linear and so forth. Okay, so what is the algorithm? Well, it has the same structure as square CB. So it has the same structure. You receive xt, you compute reward estimates as follows. You compute the distribution, the randomization distribution, sample from the distribution, observe the reward, update the model. So the differences are as follows, and they're important. So first, because data are IID, y hat, the scores are computed with offline regression, just a regression to past data, as in the work by Yunzong and David. Importantly, the weighting, inverse gap weighting, is only over a candidate's action set. So we have a more aggressive pruning. We remove the actions that we don't need to explore. And then the most tricky part, perhaps, is this choice of the parameter gamma in the inverse gap weighting function that's tuned in a very subtle way based on data. And this, opposite to what you might think, the gamma, scale is actually small if the disagreement is small. So if the disagreement is small, so for many x's, you kind of know what action to pick, then you want to decrease the step size gamma to encourage more aggressive exploration. So that's a kind of a very quick picture. Okay, and so let's see. Do I have 2 minutes, or Navid, or should I?
Sure, go ahead, please.
So okay, all right. So very quickly, so the block MDP setting is the one where you have an episodic MDP with layers. You go for H rounds, and then again for H rounds within each episode. So each episode is of length H. You choose an action, observe the reward, and then there is a state transition, right? So X now is a state rather than a context, because your action changes the state. And X is rich high dimensional, and so we cannot afford the dependence on the size of this state space. However, we assume, as done by these papers, the first one probably by Akshay authors, that there's a latent space in which we can pay size of S, and that each X uniquely maps to this latent state space S. So that means that the transitions factorize, this next state is drawn from this distribution, and then there is some emission from an unknown function of the latent state. And so again, we have function approximation, and we make this unfortunate completeness assumption, which is, I guess, common, but unclear if this is necessary, is that for all functions, the Bellman backups are contained in the class F, and that's stronger than just realizability of the optimal Q function. Okay, I'm going very fast, but just the bottom line is that there is an efficient method. I should say that ADA CB is also efficiently implementable with regression oracles. This regRL method for this block MDP setting is also efficient in terms of regression oracles, and that has polynomial dependence on state space, action size, H horizon, and the disagreement coefficient. And so this is a smaller quantity than the eluder dimension used in previous works. It could be significantly smaller. Okay, that's the definition of this value function disagreement coefficient. Importantly, this gives the fast rate in terms of the the instance dependent rate that we already observed from contextual bandits. Okay, so the hope is that one can use these disagreement coefficients as instance-dependent quantities and replace the eluder dimension in many of the results that are that have been done previously. Okay, that's the algorithm. It's essentially based on optimistic least squares value iteration, there are lots of details that Dylan worked out by convexifying this, lightly convexifying the value functions. That's an important step. Anyway, so that's a wrap up. There is this hierarchy of problems in my mind: the statistical estimation when there is a true parameter, statistical learning where it focuses on prediction, and these are becoming more and more difficult. Online learning where there's a temporal aspect, contextual bandits where you have partial information, and RL where there is state. And I mostly talked about contextual bandits, but the hope is to bring kind of the statistical learning point of view to both contextual bandits and reinforcement learning, and understand sample complexity with function approximation. Thanks.
Yeah, thank you so much, Sasha, for the wonderful talk. Very interesting results. So I know there were a couple of questions which I think you already answered. There is a question about what's the difference between block MDP and ROMDP?
And what?
ROMDP.
I'm sorry, I'm not familiar, or I'm not.
Yeah, I don't know what. Okay, let's ignore that question for now. There was another question I think earlier about the square CB algorithm, how it compares to Thompson sampling, and was there any relationship between the two?
It's very different, right? So Thompson sampling, you have parameters. So let's just think about it. Let's say you have a neural network, and what would you do if you did right? What would you do if you have a neural network? Thompson sampling would put a distribution on the weights of the neural network, somehow update the posterior, and then sample from that. I don't even know what that, what theoretical guarantees one can get from that. Here, everything is done once you've got an estimate using online or offline regression. You just do a simple randomization on top of the estimated actions, which is a very simple computational procedure. You don't need to do any Bayesian updates or sampling.
Yeah, sorry to interrupt. I guess my question is what is the intuition on why this will work? Because it seems like intuitively, if we're not very sure about our estimation, probably we want to sample more. Probably we're making some mistakes in the estimation. Probably this has higher rewards than we expected. But here it seems like as long as we're having a very low estimate of the reward, then we're going to sample it very few times as expected. So yeah, right. I mean, it sounds very different from the upper confidence bound or Thompson.
Yes. So I should say that the maybe the surprising part is that we're not forming any upper confidence bounds, which typically we don't know how to do in these rich situations with the complex function classes. And so the tail of this distribution is, in some sense, the most randomization you can do. It's a very kind of fat tail, right? So you're giving quite a bit of mass to other actions, and you're relying on the quality of the estimate. And from regression, you know that these estimates will be converging in the L2 sense. Let's talk about IID data. You know that there will be converging in the L2 sense to the true regression function. The problem is that this is L2 under your randomization distribution. And so you want that to be as kind of flat as possible. to say something about the quality of the estimates. So I don't know if I answer this or.
Yeah, so like, can I intuitively understand that the exploration is encouraged in the sense that this distribution is fat-tailed in some sense?
Yeah. So imagine you put uniform, right? So uniform is if gamma is equal to 0, right? Then you just have uniform. That doesn't look at the estimates at all, but that's not going to work, right? So you have to start tuning gamma to be higher and higher as you get more and more information with time, so that you start focusing more and more on this best action, right? But if you compare, for instance, to Boltzmann sampling drops off very quickly because of this exponential. Did I say Thomson? I meant Boltzmann sampling. Boltzmann sampling drops off very quickly because you're exponentiating the gaps, right? And this one is pretty flat, like one over the gap.
I see. Yeah. Thanks very much.
Sure, you're welcome.
Okay, we're over time. If there's maybe one more quick question, otherwise we'll wrap up. Okay, so if not, then let's thank Sasha again. Thank you so much. Thanks everyone for joining us. Next week we'll have a talk by Melanie Zulinger from ETH. And again, thank you very much, Sasha.
Thank you, my pleasure.